Welcome back, Patriots. This is a very frustrated Mr. Love, aka the Math Patriot, bringing you another fun and exciting lesson in the world of high school geometry. I say frustrated because this is the fourth time that I've recorded this lesson, and I keep on having all sorts of issues with my recording. So we are not going to be doing any of the fancy stuff today. Once again, we're just going to get this done. Now, we talked about composite figures a tiny bit last class period along with circles. We're going to continue those on today. We're going to be covering regular polygons as our major topic today. And there are only 6 examples today, but there's quite a bit of explanation. So I'm really hoping to keep this down, but I'm still expecting this to be about 30 minutes. So buckle up your seatbelts and let's go. Now, we said regular polygons. Remember that a regular polygon is one in which all the sides are the same and all of the angles are the same. So in this particular polygon, we know that BC is congruent to CD, congruent to DE, etc. Also, angle C congruent to angle D, congruent to angle E, etc. Oh, also for those of you that have the notes that I made, all of these underlined things are the fill in the blanks, and anybody who's not in my local class here, well, you just kind of watch and those underlines don't apply to you at all. So, the center of a regular polygon. Now, the center of the polygon is the same thing as the center of the circumscribed circle. Remember, the circumscribed circle is a circle that goes through all of those vertices. So the center of the polygon is the same as the center of the circle. Also, the radius that I have marked here in orange or red is the radius, AP. Now, at first, if I was just to draw a square, which is a regular quadrilateral, mark its center, and draw this, it wouldn't quite make sense of why I was calling that a radius. However, if I were to draw that circumscribed circle, you can see, yes, that is a radius of the circle. Now, our third vocabulary word here is the apophthegm, which sort of sounds like I'm trying to say a animal hanging upside down from a tree with a bad lisp, but no, apophthegm is actually correct. There is a TH in the middle. That is a segment drawn from the center to the midpoint of one of the sides of the polygon, or one that is perpendicular to it. They are both the same thing. So here I've got FP as my apophthegm, and that is perpendicular to AB as marked, and that's also the midpoint, so FB is congruent to AF. The central angle of the regular polygon is here angle APB, this angle here. Notice that it is cut exactly in half by the apophthegm PF, and I'll be taking advantage of that later on. Keep in mind that if I was to draw all of the radii, I would get exactly the same number of central angles as I get, or as I have sides. Also, all of those central angles would all be congruent. So the measure of any one of those central angles is exactly 360 divided by n. So in this particular case, if I wanted to find the measure of angle APB, that's going to equal 360 divided by 5, because n is the number of sides, which is going to equal 72 degrees. Don't believe me? Type it in the calculator and you will see that. Now, if I want to find the measure of angle FPB, which is this angle here, just cut that in two, and that's going to be 36 degrees. I know that's a lot right now that's not actually on this vocabulary section, but I wanted to go ahead and cover that because it'll save us some time when we get to one of those examples, I believe example 2 and 3. So we want to find and label all of these different things. Let's go ahead and identify the center. The center we can see is point X. The radius, we can label use any of the ones that are on there. We can say that it's XQ, also XR would have worked, either one. A central angle is, the only one marked on here is angle QXR. Now remember, you cannot say just angle X because we've also got, with that dotted line there, we've also got angle QXN and also RXN. Either way, you cannot just say angle X. Then find the measure of the central angle. Actually, you know what? I just did that on the previous slide. The measure of angle QXR is 360 divided by n, number of sides, which is 5, which is 72 degrees. All right, number 2, what is the area of this regular hexagon to the nearest tenth? We'll be using our calculator to go to the nearest tenth, and we will be rounding if necessary. So I'm going to go ahead and point out that the way that I'm going to do this one is not the same way I'll be doing the rest of them. I'm just going to point out how we could utilize these triangles in order to come up with the area of the polygon, and then I'll show you the shortcut when we get to the formula on the next slide. So since this is a regular polygon, I know that all the sides are congruent, meaning that in particular, this side is 2 feet. Now, the area of this one triangle here is going to be, area of the triangle is 1/2 times its base times its height. Now, the base of it is 2, and the height of it is 1.5. Now 2 times 1/2 is 1, times 1.5 is just 1.5 feet squared. Now, we know that every single one of these triangles is going to have the exact same area because they all have the exact same side of 2 feet and they have the exact same apothem of 1.5 feet, which means that the area of the hexagon is going to equal the number of triangles, 6, times the area of each triangle, which is 1.5 feet squared. Then we're going to multiply that through. Well, 1.5 times 5, actually that's just 9. I don't need the calculator today. That's just going to be 9 feet squared. I say I don't need the calculator. Remember how I said this is the 4th time I've recorded this? I've got a lot of these answers memorized. Let's make that a T. Now this method of finding the area of each individual triangle and then adding them all up or multiplying by the number of triangles, that is perfectly valid. You could do that every single time if you want, or we could jump into our shortcut. And I'm not going to spare you the derivation of this, but essentially what we're going to do is take 1/2 times the apothem times the number of sides times the length of each side. So if we know the apothem and one side length, I can find the area. You also notice here that this n times s, number of sides times the length of the side, is nothing more than the perimeter, which is why we have this version on the right. 1/2 times A times P, 1/2 times apothem times perimeter. And those two are the ones that I'm going to be using for our next 2 examples. Now, I'm going to go ahead and warn you, some of you are not going to enjoy examples 2 and 3 because we're going to be bringing up one of our old friends from Unit 7, trigonometry. So before we move on, I know I'm going to have it, so I'm just going to go ahead and write SOHCAHTOA up here on the top so that we can use it when we need to. Now, this is a pentagon. I want to find the length of AB. Now, in order to do that, I'm going to need to find first the length of DB. So I'm going to go ahead and draw this triangle out here. This is 9 centimeters. And in order to find the area of the pentagon, it's 1/2 apothem times perimeter. So I need to know the apothem, which is here, which came from there, and then also the length of each side. Now, if I can find this one, I'm just going to label it B. I can multiply B times 2 to get the full length of AB. So our first step is going to be solving for A and B. Now, this is where our trigonometry comes in because we've got this. Oh, actually, I haven't got there yet. The central angle here, we've already done that on the previous slide. That was 72 degrees. That was 360 divided by 5. And then this angle, half of that is 36 degrees. So here we've got 36. And now we're ready for trigonometry. So I can label these. 9 is my hypotenuse. A is my adjacent side. That worked out nice. And then B is my opposite side. So let's solve for our apothem first. Adjacent and hypotenuse makes cosine. So cosine of 36 is equal to A over 9. Now we're going to cross multiply. A is equal to 9 cosine 36. And as always, when we go to do this, make sure your mode is in degrees before you do anything else. 9 cosine 36. My apothem is 7.28, and I believe that is centimeters. Now let's find our value of B. Let's see, B is opposite and 9 is hypotenuse. Opposite hypotenuse makes sine. I'm looking up here at SOHCAHTOA to determine that. So sine of 36 is equal to A over 9. Cross multiply gives me A is equal to 9 sine 36. Ooh, I've been using A's there. Those are B's. So B equals 9 sine 36, which gives me 5.29. Now, if that one is 5.29, then I'm going to double it to find the entire side, which I'm going to label here on this side that I'm marking in green. That's just 5.29 times 2, which is going to be 10.58. And you know what? Because I've actually got a side length and not an actual perimeter here, I'm actually going to use the other version of the formula. 1/2 times A times N times S. Number of sides times side length. So that gives me A equals 1/2 times. Apothem is 7.28 times number of sides is 5 times the side length 10.58. And now I just type it in. 0.5 times 7.28 times 5 times 10.58. Let's make sure I got that right. 10.58, 5, 7.28, and 1/2. Yes. So my area is 192.56, not feet, centimeters squared. So not too bad. We're just having to pull in a lot of our previous stuff from previous units, particularly trigonometry, and then being careful with everything. Notice that I'm being very careful with the way that I'm labeling everything and organizing it. Try to do the same. All right, example 4, find the area of this regular polygon. Now this one gives me the side length is 10. So since I have the side length, I believe I'm going to go ahead and use 1/2 times A times N times S. Now let's see if we can figure out how long the apothem is. Now, if the whole side length is 10, then this small piece here is 5. So I'm going to go ahead and put my 5 in for my small triangle. Now I've got to determine the measure of this angle up here. So I'm going to look at the number of sides. N equals 1, 2, 3, 4, 5, 6, 7, 8. We've got an octagon here. So the measure of the central angle, the whole central angle, is going to be 360 divided by 8, which that one is going to be 45 degrees. Then that gives me the whole thing. Half of it, which is this piece, is half of that, which is going to be 22.5. So now we're set up for our trigonometry again. So here is our hypotenuse, here is our adjacent, and here is our opposite. I'm needing to determine my adjacent. I had no opposite. That makes a tangent problem. Tangent of 22.5 is equal to opposite over adjacent, or 5 over a. Now this is one of those. We're going to cross multiply it, and divide is going to give me a is equal to 5 divided by tangent of 22.5. 5 divided by tangent 22.5. So my apothem is equal to 12.07. Now I can take that and plug it in up here. Area is 1/2 times apothem, 12.07, times number of sides is 8, times the side length, which is 10. And now let's get that plugged in. 0.5 times 12.07 times 8 times 10. Area equals 480. And let's get our units on there, inches squared. All right, that is all of the regular polygons we're going to do. We're going to jump over to composite figures. Like I said, we covered this a little bit last time. Composite figures are just a figure that can be separated into regions that are basic figures. So to find the area of the composite, we're going to separate into its basics and then add or subtract them as necessary. Last time we were doing this whole sort of thing where we had all that stuff going on. I believe it's actually more of a semicircle, and then I had stuff like that cut out of it. In that case, it was the semicircle minus the two semicircles. You can do the exact same thing with adding up pieces as well. So on this one, it looks like I've got a rectangle as my greater overall shape, and then I'm cutting out a semicircle. So first thing I need to do is find the area of my rectangle. Area formula for a rectangle is base times height. Looks like my base is 50 times my height is 30. 50 times 30 is 1,500 feet squared. Now I want to find the area of my semicircle. The area of the semicircle is going to be 1/2 pi r squared. So I got to figure out what my radius is. Well, if this entire distance is 15 or is 30, then my radius is 15. So this is just area equals 1/2 times pi times 15 squared. Jump to the calculator. 0.5 pi times 15 squared. 353.43 feet squared. And now the area, and I'm going to use C for the composite figure, is just going to be the area of the rectangle minus the area of the semicircle. I guess I probably should have labeled that one as my semicircle. So which means that it is 1,500 minus 353.43. Well, it would help if I could hit my 0 twice. Minus 353.43. 1,146 point. Now I wanted nearest tenth, so I'm going to do 0.6 feet squared. All right, one more example. We're only 20 minutes in, going faster than I thought. Find the area of the figure, round to the nearest tenth. So I gotta decide what all I'm doing, or what all I'm going to be doing as my basic shapes here. I see two basic approaches to this. I could find 4 different areas. I could find the area of triangle 1, triangle 2, rectangle, and semicircle, and then add all of those together. Or, I think the actual easier route, excuse me, I got some hiccups, is to treat this entire shape down here as a or up here as a trapezoid, and then treat this as a semicircle. So just add trapezoid plus semicircle. And I think I'll do that. My pen's already orange, so I'm going to do the semicircle first. Area of the semicircle is 1/2 times pi r squared. Now, if the full distance of this rectangle is 18, that means my diameter is 18, therefore my radius is 9. So that's 1/2 times pi times 9 squared. 0.5 pi 9 squared. (127.23 feet squared) is the area of the semicircle. Now for the area of the trapezoid. Area formula is 1/2 times base 1 plus base 2 times the height. I'm doing that from memory. I may have written that in a slightly different order on the last unit, but it's all the same thing. 1/2 times, now base 1 is either of the two bases. I'm going to use that as this top edge all the way across here. Looks like I've got 18 plus 5 plus 5, so that's 28, plus base 2, which is this one that I labeled as the diameter of that circle, which is the same as the rectangle on the other side, so that is 18. And then my height, vertical height here is 8. So 0.5 times 28 plus 18 times 8 gives me 184 feet squared. Now to find my composite area. Area of the composite is just area of the semicircle plus area of the trapezoid. So let's plug those in. 127.23 plus 184. Plug it into my handy dandy calculator. And that is 311.23 feet squared. Well, that's all we got for you today. This is Mr. Love signing off. As always, stay patriotic.